My name is Bárbara Maia. Welcome to Sciences News. Bose-Einstein condensates, the future of modern physics. Bose-Einstein condensates are considered to be fluids in the quantum regime, highly controllable, whose behavior is not only restricted to atomic dimensions, but also manifest themselves at the macroscopic level, and which are obtained when a gas, a collection of atoms, has its temperature cooled to almost the absolute zero. Bose-Einstein condensates are conceptually very simple systems. The behavior of the system is dictated by some components. The energy of motion, which is called kinetic energy, which the cooling makes practically zero. The potential that confines it, that is, the spatial region where they are produced, which is equivalent to the reservoir where our gas is stored in the classical regime. This confinement can be modified and adapted with the use of laser and magnetic fields to meet the needs of the study that is to be performed. When the set of atoms reaches the condensate state, the atoms lose their individuality and begin to behave as a single entity. That is, there is no longer the behavior of a set of atoms, but a single one for the condensate. In this regime, there is no longer any way to distinguish the atom's individuality. The research developed by the CePOF research in Bose-Einstein condensates focus mainly on the study of turbulent regime. Turbulence, in particular, is an extremely interesting problem because it is a problem that has not solution yet. Quantum turbulence is one of the few problems where the quantum system is easier to understand than the classical system and may allow the understanding of the topic as a whole. Professor Emanuel Alves de Lima and one of the lead researchers in the field say that Professor Vanderlei Banhato and the team have been studying turbulence in Bose-Einstein condensates not only to understand the phenomenon itself, but amid a possible future applications and expanding this understanding to turbulent system in the classical regime. The scope is very large. So, the idea of the studying turbulence at CePOF is to understand how systems out of equilibrium work. It's always very difficult to predict the results of research with Bose-Einstein condensates because they are currently at the frontier of knowledge in atom physics. Methods developed by CePOF researchers allowed encoding complex images in high resolution in a laser beam. Researchers Professor Sérgio Muniz and master studying Pedro Faleiros, both from the Laboratory of Quantum Technology of the Institute of Physics of São Carlos of the University of São Paulo, have developed a method capable of controlling with greater speed and precision the distribution of light intensity of a laser beam. The technique, published in an international conference and recently highlighted in New Science and FAPESP magazine, was initially applied to encoding of a high-definition image in a laser beam. As a result, instead of generate a narrow and focused bright spot, as a laser pointer does, the projection of this type of light manipulated by the developing approach allowed the formation of a super-realistic portrait of a feline produced with laser light. The first experiment is what scientists call a proof of principle, to show that the new technique is capable of producing complex patterns with high resolution and richness of detail. The same technique can be used to generate any other pattern programmed into the system built by the researchers. In the laboratory, the research had the laser beam reflect into a device called a spatial light modulator, SLM, built with programmable liquid crystal. Which pixel in this device is controlled by electric fields programmed into a computer. In this way, the scientists modulate the phase and control the interference of the light intensity point by point, and are able to distribute the light into the pattern they want to produce. The high level of light control achieved with the experiment may be used for improved so-called optical tweezers. This device uses laser to grip and move microscopic objects such as nanoparticles, atoms, molecules, and Bose-Einstein condensates. The initial motivation for the new technique was in the quantum simulation with ultra-cold atoms and the control of nanoparticles with optical tweezers. But the method can be used in the other application, such as controlling the profile of a laser beam and the microfabrication of laser structures. The researchers say that the method allows the light of the laser beam to be controlled without the need for complex computer algorithms. But more research is needed to extend and demonstrate the full application of potential of this approach. The method developed as well as the researchers involved is part of the Laboratory of Quantum Matter and Technology located in São Carlos Physics Institute at the University of São Paulo, and part of the Center of Optic and Photonic Research, CePOF. Currently, the group has several experimental systems, as well as a theoretical and computational studies, a means to study the quantum properties of matter and the applications of new quantum technologies. Want to know more about science? Then don't miss the next Sciences News.